I wanted to work through an example of calculating the capacitance of a capacitor. In this particular case, we're going to calculate the capacitance of the cell membrane, which is a natural capacitance. So there are man-made capacitors that we use in electrical circuits. For example, our phone involves many man-made capacitors that typically are pico or nanofarad capacitors, but there's also lots of natural capacitors in our world. The Earth is the biggest capacitor in our world. It is a capacitor that stores charge with a potential difference. Also, a thundercloud and the ground form a capacitor that stores charge too, with a potential difference between the ground and the thundercloud. But at a more microscopic level, cell membranes are capacitors. Axons, neurons are capacitors. And so we're going to think about a typical cell, and we're going to figure out the capacitance of its membrane. I pictured the cell over here on the left-hand side, and then an abstraction of the membrane over here on the right-hand side. So if you think about a cell, it's a bag of salty water surrounded by an ocean of salty water, where there's different concentrations of the salts inside the bag and outside the bag. And the inside fluid and the outside fluid are separated by some thin membrane or thin film. It's a fatty lipid membrane. So we've got a inside conductor, a outside conductor, the intra and extracellular fluids, and then we've got an insulating medium in between the lipid membrane, and that is a capacitor. And so the inside fluid, outside fluid can store some charge, and they will create a potential difference, electrical field across the lipid membrane. And again, it looks exactly like a capacitor. So let's see if we can find the capacitance of this cellular capacitor. I pictured the cell over here on the left-hand side. So I'm going to imagine a cell that is a perfect sphere, and it has a radius of about 100 microns. And the thickness of the membrane is about 10 nanometers. And actually, we're going to calculate more than just the capacitance of the cell capacitor. We'll also calculate we'll calculate the charge on the plates of the capacitor when there's a resting voltage of 70 millivolts. We'll calculate the field across the lipid membrane when there's this resting voltage of 70 millivolts. So we'll do a couple of other things beyond just figuring the capacitance. Once we got the capacitance, we can figure in interesting things like the amount of charge it's storing, like the electrical field across the membrane. Now I'm going to abstract the spherical capacitor to a parallel plate capacitor, because we know some formulas for a parallel plate capacitor. In particular, we know the formula for the capacitance of a parallel plate capacitor in terms of the area of the capacitor and the separation of the plates in the capacitor. What I'm effectively doing here in this abstraction, you might think, how can I do this abstraction? I'm imagining taking the spherical cell on the left-hand side. I'm going to snip it open with my scissors, and I'm going to spread it out flat. And I'm going to spread it out flat so I get these two sheets. The faces of the sheets are the inner and outer edges of the lipid membrane. And so that's my abstraction on the right-hand side. The area of the surface of the parallel plate capacitor is now the surface area, was the original surface area of the sphere. So that's what the area is. And I calculated this approximately 10 to minus 7 meters squared by just 4 pi times the approximate radius of 100 microns. So I just made a round number that is approximately that. And then the separation, right? The separation was this thickness of the lipid membrane. So the charge is on the inside and the outside of the lipid membrane. And that separation was 10 nanometers, and that's 10 to the minus 8 meters. So this is the geometry of the capacitor in the cell, abstracted a little bit from a spherical shell to a parallel plate capacitor. And again, we said that there's resting potential between the inner and outer walls of the membrane is 70 millivolts or 0.07 volts. So I wrote that down again. So this is the physics problem that we are handling. This was the original molecular biology cellular problem that we were thinking about. So what's the capacitance of the cell? Well, we can use the formula for the capacitance of a parallel plate capacitor. If you remember it, it's pretty straightforward. It's the electric permeativity of free space multiplied by the area of the plates in the parallel plate capacitor divided by the separation between the plates in the parallel plate capacitor. It goes up, the capacitance goes up with the area, because the bigger the area, the more space you've got to put the charges. It goes down if you increase the separation, because to increase the separation of a positive and negative charge, to increase the separation of the plates, you've got to push, you've got to do some work. So this makes it, increasing D makes it harder to store charge, increasing A makes it easier to store charge, hence capacitance is A over D. Epsilon naught is this constant, like Coulomb constant, characterizing strength of electric forces, strength of electricity. Its value, we're working pretty approximately here, it's about 9 times 10 to the minus 12 in SI units. I've written it, those SI units, as farads per meter. There's other ways that you can write the SI units for epsilon naught. This is actually the simplest way, and this way is farads per meter is easy to remember if you remember this equation here for the capacitance of a parallel plate capacitor. If you remember this equation for the parallel plate capacitor, and you know that the units of capacitance are farads, I never forget that. And if you remember that area has the units of meters squared, and distance has the units of meters, I'm never going to forget that. Meter squared over meters is meters. It must be that epsilon naught, if there's going to be a valid physics equation, the units on the left and the units on the right must be the same. It must be that epsilon naught has units of farads over meters. So that's the way I remember the units, the simple way of remembering the units of epsilon naught as farads over meters from this equation for the capacitance of a parallel plate capacitor that I don't forget. Okay, so let's plug in the numbers. The capacitance for our cell then is going to be 9 times 10 to the minus 12 farads over meters. That's epsilon naught. Multiplied by the cross-sectional area of the plates, that's 10 to the minus 7 meters squared. And remember, we're just working approximately because all cells are different. We got to divide by the separation between the plates. This is 10 to the minus 8 meters. So if we look at this equation here, we got 9 times 10 to the minus 12 multiplied by 10 to the minus 7 over 10 to the minus 8. That's just 10. That's just 10 meters, this ratio here. And so we just got to multiply this number by 10. And so this comes out to be 90 picofarads farads. A pico is 10 to the minus 12 of a farad. So it's 90 times 10 to the minus 12 of a farad, which is 9 times 10 to the minus 11 of a farad. So that's the capacitance. If we want the charge that arises from the salty fluid on the inside, salty fluid on the outside of the cell membrane, the charge on the plates, we can calculate the charge on the plates using the master equation for a capacitor. Master equation for a capacitor is C, the capacitance, equals Q, the charge on the plates, divided by V, the voltage between the plates. So C equals Q over V, which means Q equals CV. I'm just multiplying both sides of the master equation by the voltage difference between the two plates. Now we know C now is 90 picofarads, so that's 9 times 10 to the minus 11 farads. And we know V is 70 millivolts, or 0.07 volts. And if we multiply those two numbers together, I'm going to get, I worked it out already, 6 times 10 to the minus 13 coulombs. 6 times 10 to the minus 13 coulombs. That's 0.6 picocoulombs. Now, this is a very small amount of charge. It's order 10 to the minus 10 to the minus 12 coulombs, but it's a very large number of ions, of positive and negative ions that must be layered onto the inner wall and the outer wall of the membrane. So one membrane is positive, the other one is negative, and there's a lot of ions. In fact, you think about the electronic charge being 10 to the minus 19 coulombs, and this is 10 to the minus 13 coulombs. This is a million times, more than a million times bigger than the electronic charge of an electron or a proton. And so there are millions of ions layered on the inside of the membrane, layered on the outside of the membrane to make this charge and to make this resting voltage of 70 millivolts. So that's interesting to figure out. One other thing we can figure out is, what is the field? So there's all this positive and negative charge on the inner and outer membrane. So that means there's electrical field between the inner and outer walls of the membrane through the fatty lipid layer. How big's the field? Well, remember the field, I'm just going to figure the strength, the field, not the direction. Remember the field is the negative slope of the potential. It's the change in potential divided by the difference in space over which that change of potential occurs. So again, I'm just figuring the size. So I'm just going to divide the size of the voltage, 70 millivolts, by the separation between the charges on the inner and outer walls. That's the thickness of the membrane. So we got 70 millivolts, so that's 0.0 volts, divided by the separation was 10 to the minus 8 meters. It's 7 times 10 to the minus 2 volts divided by 10 to the minus 8 meters. And so that actually comes out to be a large number, because we got a smallish number divided by a really, really small number. It comes out to be 6 times 10 to the 7 times 10 to the 6 volts per meter. That's an enormous electrical field. Because the charges are so closely spaced, the positive and negative charges, because the membrane is so thin, that electrical field, due to those millions of charges, is actually a very strong electrical field. It's much stronger than the electrical field even between the ground and the earth for a thunderstorm. So it's a very large electrical field. It reminds us that the cell is an electrical environment. You don't want to think of the cell as sort of living in a gravitational world. You want to think about the cell as living in an electrical world. And here's the cell is a capacitor. Here are the voltages and the fields and the charges that are the electrical nature of the cell.